Hello and welcome. In this video, we're going to take a look at a very important concept for both pre-calculus and calculus and kind of upper level math in general is looking at distributing and factoring. So we've already looked at how to use the distributive property for real numbers, but now what happens if you maybe have polynomials, maybe 2 or 3 terms each, and you want to have multiple of those multiplied together? Maybe you want to distribute and simplify. Or maybe you have a polynomial with several terms and you want to make it look simpler by factoring it, and then maybe from there you can cancel. Both of these things are going to be very, very common in pretty much all of the future sections. So we'll cover this and give you a couple basic tips as to maybe a few strategies as how to factor, what kind of shortcuts there are for common expansions and things like that. So take a look at the notes here, and we'll start off with the distributive property. And the distributive property can be used from left to right. So if you have A multiplied into B plus C, then you can distribute from the left and have AB plus AC. The distributive property from the right, if I have, say, B plus C multiplied by A on the right, then it works out the same way. You can distribute in from the right-hand side. Now, I'm going to start making this a little bit more tricky, where instead of having 3 individual real numbers, we can actually apply this concept to polynomials. And let's start off with polynomials with 2 terms. So those would be called binomials. If I have A plus B multiplied by C plus D. Okay, so there's 2 terms, and we're taking 2 of those and multiplying them together. So what I could do is I could apply the distributive property from the right and take this C plus D and multiply that into the brackets on the left-hand side. So C plus D will get multiplied on the right-hand side by A. C plus D is going to get multiplied on the right-hand side by that B as well. And from here, I can then use the distributive property from the left, and I can use that property twice. And that gives me AC plus AD plus BC plus BD. Okay? So in the end, you actually end up with 4 terms, because when you distribute across a binomial, you get 2 terms, and we're distributing twice. So that ends up with 4 terms now. Now there is a little shortcut for this that you might be familiar with. See that our original terms here, A plus B, C plus D, you might be able to shortcut this process a little bit by knowing that there is a basic way to memorize this result. So the A and C are the first values in both sets of brackets. We're going to be multiplying those together. And because that's the first in each set of brackets, we can denote that with an F. It's the first terms. And we see that A and D need to be multiplied together. Okay, so A and D need to be multiplied together. Those happen to be the outside terms in both sets of brackets, so we can denote that with an O for outside. B and C need to be multiplied together. Those 2 values are the inside terms in both sets of brackets. Denote that with an I for inside. And then B and D need to be multiplied together. Those would be the last terms in both sets of brackets. So we can denote that with an L for last. And you end up with this little shortcut, this acronym, FOIL. And that is only there to help you out when you multiply a binomial, and that's 2 terms, times another binomial. Okay, so FOIL, or you can use it as a verb, foiling it out if you want. That is only applicable when you have 2 terms times 2 terms. But you can apply the distributive property as far as you need to. All right, so if you wanted to, you can essentially do the same thing here. You would take C plus D plus E and multiply that onto the A plus B. And then once you've done distributing from the right, then you can start doing all your distributing from the left. And you're going to end up with even more terms this way. And once you have all of these things expanded, don't forget that if there are any of the terms that have the same properties, if they are like terms, like if you see 3x and 5x, then you can add them together and get 8x. Don't forget that you also want to simplify. Now, there are some very, very common things that we often end up expanding out. So I'll give you a list of 5 sort of special formulas for expanding things out, especially if you ever have a binomial like a plus b and you want to square it. That's going to happen a lot, and so you might want to remember a couple of these handy shortcuts. All right, here are 5 basic products that we might want to expand out, and all of these are binomials. Now I'm using capital A's and capital B's just to kind of be placeholders for the 2 terms, and a term, like a capital A, could be a little bit more complex. Maybe A in your scenario is 5x squared, and that whole thing is capital A. A and B are just whatever is on either side of that plus sign. Those are the 2 terms I'm talking about. Now, these 5 special product formulas, they're kind of in the order in which I think is probably going to be the most useful. This first one here comes up a lot. If you ever have something plus something, those are 2 terms, A plus B, and you have the exact same 2 terms in the second set of brackets, but with a minus sign, then it's pretty nice when you expand this out. And you can try all of these out for yourself. You could expand and then collect like terms, and you'll end up with A all squared minus B all squared. Now the next one down is A plus B all squared. Now, whenever you see that, remember A plus B all squared is the same thing as just writing A plus B times another A plus B, and then you have to expand that whole thing out by distributing twice. Or if you remember FOIL, then you can use that technique. So you end up with 4 terms if you expand that out, but 2 of them you can collect together, and as a result, you end up with A squared plus 2AB plus B squared. And you might want to remember that one as square, double the product, square. It's A squared plus 2 times the product of AB plus B squared. And the next one down is more or less the same, but because there's a minus sign in there, A squared minus 2AB plus B squared. That is also square, double the product, square, except that when you have negative B times negative B, you end up with a positive B squared. Now number 4 and number 5, these ones are also fairly similar. It's not quite as obvious as number 2 and number 3. You'd actually have to write out A plus B times A plus B times A plus B. And you have to distribute several times and then start collecting terms. So it's actually a lot of expanding just by distributing. And this is where it might be handy to remember this special product formula. If you expanded it out enough times, you'll end up with an A cubed. Now hopefully that part's somewhat intuitive. But you end up with 3 A squared B's, if you add them all together, plus 3 AB squareds, plus B cubed. And you can try that out for yourself. We already know what A plus B squared is, using square double product square. Just take that and multiply by another A plus B and then distribute. You'll get that same special formula after you simplify. A minus B cubed, also fairly similar. You'll have an A cubed, but then you also have minus signs in here. Negative 3 A squared B plus 3AB squared minus B cubed. Okay, so I would say that as you go down that list, you may use these a little bit less frequently. It's really good to know some of these sort of shortcuts. Now, remember, like I said, Capital A and capital B are just sort of placeholders for whatever that term happens to be. So if you have 2x squared minus 5, and that was all squared, and you can remember your square double product square, then you can actually just say, well, the first thing in there is 2x squared, so it's 2x squared all squared. That's the square. Double the product, so that's going to be 2 times 2x squared and a 5, and because it's a minus sign, that's going to end up being negative, plus negative 5 squared. So I'm just using formula number 3 there. That makes sense, and then you can go ahead and you can start simplifying exponents. The 2 must be squared to get 4, and x squared squared is going to be multiplying exponents, so that's x to the 4. And then you're going to have to multiply coefficients here. A negative 2 times a 2 times a 5 is negative 20, x squared, and then 5 squared is 25. So it's a little bit of tidying up at the end after you've applied the special product formula. Right, now these special product formulas can go in both directions. If you're taking what we have on the left-hand side as being brackets and multiplication, and going and using a substitution to replace with what's on the right, then this is what we call expanding or distributing. So that's useful because you might want to expand and then collect like terms. But you can also use these formulas in the reverse direction, and that would be factoring. So if you're lucky enough to see something of the form a squared minus b squared, then you can factor it and just say that that is equivalent to writing a plus b times a minus b. And an example of that, if you ever had x squared minus 4, then that is a square minus a square, and then you can use the special product formula to factor that x plus 2, x minus 2. That's using rule number 1, but using it in the reverse direction. Okay, well, let's take a look at a few different strategies for factoring. If you don't happen to have exactly one of those special product formulas, here are different ways that you could factor a polynomial with several terms. All right, our first strategy is if you have a polynomial, that's, several terms, look for something that's a common factor of every term. And I'm putting this strategy as number 1 because it's really usually the first thing you would look for. This might be the most obvious if there's something that every term seems to have in common. Okay, here's an example. Okay, here I've got 3 terms. Now, we said that 2 terms was a binomial. If you have 3 terms, that's called a trinomial. And in each of these 3 terms, you're trying to look for a factor that they all have in common. So we can look at the coefficients first, 8, 12, and 4. Now it's a negative 4, but 4 does go into all 3 of those. So we can either factor out a 4, or we could factor out a negative 4 if you wanted to. Factoring out a negative means that you're going to have a lot of signs get flipped to the opposite sign. In this case, it might be easiest for us just to factor out positive 4 and keep all of the signs exactly the same. So that's one thing we're going to do. I'll write an equal sign just below this here, and we know that 4 is something that we can factor out of everything. I'm going to get ready with a big bracket here to leave room for the 3 terms that we're going to factor 4 out of. Now, since we're factoring out a positive 4, that's going to keep the signs the same. So we'll have a positive term plus another term, and we'll still have minus a third term. So that won't change the signs. But if you want to factor out a negative 4, then you'll have to flip the signs of all 3 terms. All right, now looking at the next factor in each term is we have several factors of x. Now, x to the 4 is 4 factors of x. The next term has 3 factors of x, and the third term has 2 factors of x. And we can only factor out 2 factors of x. So that means x squared. Looking at the y's, if you just look at the exponents now, we have y squared, y to the 5, and y to the 5. So looking at the lowest power of y is y squared, and that would be as many factors of y as we can see common amongst all 3 terms. All right, now let's take a look at what we have left. If you have 8 and you factor out 4, you're left with 2. Just think of it like division. X to the 4, factor out x squared. Okay, that's going to remove 2 factors of x. Left with x squared. Y squared, if you factor out y squared, then you've factored out all of the y's, and there aren't any left in that term, which leaves you with a 1. But we don't have to write that 1 because 1 times 2 is 2, and that is our current coefficient. The next term, we have 12. If you factor out 4, again, just think of it like division, it's going to give you a 3, because 3 times 4, when you expand, give you back 12. Take away 2 factors of x, you're left with a single x. And since we have y to the 5 and we're getting y squared factored out, again, you can think of this like division. Y to the 5 divided by y squared is y cubed. There are 3 factors of y left. And then last but not least here, from this last term, we have a negative 4. And if you factor out 4 from that, you're left with a negative 1. But we don't tend to write 1s as a coefficient. X squared is completely factored out as well, so we don't have to write any powers of x. It doesn't make much sense to write x to the 0 because that is also just equal to 1. But we have y to the 5 again, and we've already seen that y to the 5 divided by y squared leaves you with y cubed. And you can see that we've taken away a lot of the garbage and we've stuck it out in front of the brackets, and we still have a trinomial inside the brackets. You're not losing any terms, but each term is a little bit more simple. All right, now let's take another look at strategies 2 and 3, which are also really specifically to do with trinomials. Okay, the next strategy here is specifically to do with quadratic trinomials with a leading coefficient of 1. So first of all, what does that mean? Well, we know it's a trinomial, so there's 3 terms here. And you can see we've got 3 different terms that you cannot say are, you can't collect. There's nothing in common with them. So the first term here has an x squared. And because x squared is the highest power of all 3 terms, that's what makes this polynomial a quadratic. So that's the leading term. It's the first term, but it's also, we call it the leading term because it is the highest of all of the powers of x. So that's what makes this a quadratic. The term after that is just an x, and that's considered linear. It doesn't have a square. And the third term there is just a constant. So because the highest power is quadratic, that's where it gets its name. It's a trinomial, 3 terms. And this part with a leading coefficient of 1, that's because the coefficient, the number in front of the x squared there, is actually a 1. We haven't written it down. The other coefficients, b and c, can be anything you like. Okay, so if you have something of the form x squared plus bx plus c, it is quite possible that we might be able to factor that. And ideally, we could factor x squared plus bx plus c into something of the form x plus or minus something plus r, and x plus or minus some other number. R and s might be negative, I don't know. Ideally, that's what we want it to look like if we can factor it. Now, to come up with a shortcut for finding r and s, let's suppose that you can factor it. And then if you wanted to check your answer, we'll expand it back out and see what you get. So expanding the right-hand side out here using FOIL, first times first, x squared, plus the outside, x times s. I'll put the s in front since that's going to be some number. R times x and r times s. Now, both of the terms in the middle have an x. That's a common factor of those 2 terms. So using some factoring of a common x, we can write that as s plus r times x. Okay, now matching the left-hand side to the right-hand side, if you are able to factor it, then you can match coefficients. B must equal s plus r. So that's one requirement for factoring it this way. S plus r are 2 numbers that, when added together, equal the coefficient of the middle term. And matching coefficients at the end here, the constant if this is possible to factor it this way, then we must have that r times s is equal to c. Now, just for convenience, I'll change this from s plus r to r plus s so that everything's kind of written in the same order. So what you can do if you're trying to factor a trinomial into two binomials like this is you're going to be trying to figure out what is r, what is s, so that those two numbers satisfy these two requirements. R plus s must add up to the coefficient of the middle term, and r times s has to equal the constant term. So just as a quick example here, suppose that we have x squared plus 9x plus 18. And I've written things in the same order as what I was showing you, as it's a monic or a leading coefficient of 1, quadratic trinomial. So you can see this is essentially the b here is 9 and the c in this case is 18. So I don't know what r and s are, but I want to find two numbers. The first one could be r, the second one could be s. Find two numbers that when added together they equal 9. And those same two numbers when multiplied together have to equal 18. So you try to think about that for a little while and remember that these r's and s's, they can be negative. And it will be a lot more obvious when you look at the product. If two things multiply together equal positive 18, then these two numbers are either both positive or they are both negative. Now, look at the 9. You can't have two negative numbers add up to 9, so they must both be positive. What are the factors of 18? 1 and 18, well, they don't add to 9. 2 and 9, well, they don't add to 9. So keep working your way through the list. 3 times 6 equals 18, and 3 plus 6 equals 9. And there you go. We found our two factors. So you could say r is 3 and s is 6, or you could say r is 6 and s is 3, and it won't matter. But now that you found those two numbers, we can factor this and say x plus 3 times x plus 6. And you can check by distributing that does in fact give you x squared plus 9x plus 18. All right, so this strategy revolves around a little bit of guessing and checking and seeing if you can find two numbers that add up to the middle coefficient and the two numbers must multiply to the constant term. Just make sure that you've got it written in x squared plus bx plus c form before you try this. All right, this third method is also for quadratic trinomials. So again, an x squared is going to be looking like your highest power of x and 3 terms. But this time, the coefficient in front of the x squared can be anything. So I've written that down as an a. It could be a 1, in which case then you can go and use the second method we just looked at. Or if it's not a 1, then this will be a little bit trickier and there are several steps to try to follow. Now in this case, it might be easiest just to try to follow along with an example so you can kind of see how about, now in this case, it might be a little bit easier just to try to follow along with an example to see how this works. Let's suppose we have 6x squared plus 7x minus 5. Okay, so matching up is important here. Make sure that things are in the correct order so you can see that a is equal to 6, b is equal to 7, c is equal to negative 5. Any of these three values, a, b, or c, could be negative. Now, in order to try to factor this, you can imagine that hopefully in the end, we'll end up with a binomial times another binomial. Something of the form a plus b times c plus d, all going well. Now remember that when you have two binomials multiplied together, you can use FOIL. That means you have 4 terms. However, we only have 3 right now. So we use a strategy called the AC method. And the AC method is used to take these 3 terms and actually break one of them into 2 terms so that we end up with 4 terms. So here's the AC method, step by step for this example. It's called the AC method because what we're going to be looking at in particular is A and C, in this case 6 and -5. When you multiply them together, you get 30. So AC is the first step. 6 times -5 equals -30. Now, much like in our previous strategy, look for two values that when you add them together, you end up with the middle term, which is 7. And this time, when you multiply the two values, you want it to equal AC, which is this number 30 in this case. And again, it's a little bit of guessing and checking. The two things must add up to 7. Now that leaves tons of possibilities considering that one of these numbers can be negative. What's a little bit easier to look at is finding the factors of -30. 1 and 30, 2 and 15, 3 and 10. And then when you get to that point, remember that one of these numbers has to be negative because they have a negative product. And if I have a +10 and a -3, they do add to 7. All right, that's where the AC method gets its name. But that is about as much as you need to know about why it's called the AC method. The next step after this is to take the trinomial with 3 terms and actually expand it into 4 terms. And this is called decomposition. So, first step in the AC method is this guess and check. Once you've been able to successfully guess the two values, the next step is called decomposition. Decomposition is where we take our trinomial and we take that middle term 7x and we split it up into 2 like terms. Usually we do the opposite and we collect like terms, but what we're going to try to do here is actually have 2 terms to work with. So 7x is the same thing as 10x minus 3x. And those are the 2 values that we just were able to find in step 1. Now you've got 4 terms to work with. And the next step after decomposition is called factoring by grouping. In factoring by grouping, what we are doing is we're going to look for just basic common factors, kind of like I was discussing in the first strategy. But in this case, we're going to be looking for common factors in 2 groups. 6x squared plus 10x is going to be one group. -3x minus 5 is going to be the second group. And when we're looking for common factors, we're going to see what we can pull out of 6x squared and 10x. Looking at the coefficients, we can definitely pull out a common factor of 2, so we'll do that. Now you can pull out a -2 if you'd like, and that's going to change the signs. But let's try to see if we can do this with a +2. Pulling out an x is also the highest power that we can pull out from x, and we'll end up with 3 and an x from the first term, and the second term, 10x, well, I guess that's going to be just leaving us with 5. Now, looking at the second 2 terms, it doesn't seem like there's very much in common between 3x and 5. There's always going to be one number that everything has as a common factor, and that's the number 1. So I can factor out a 1 from anything you want. But if I factor out a -1, then I can start to change those 2 negative signs into 2 positive signs. So if I factor out a -1, I'll end up with a +3x and a +5. Now, so far, because of our AC portion, where we looked for the 2 numbers that added to 7 and multiplied to -30, it's not just luck. Once you found those 2 numbers, you should end up with 2 common factors again, 3x plus 5. And that leads us to step 4, is factor once more, but in this case, factoring out the common binomial. Now, what if you didn't end up with a binomial that both terms have in common? Well, then you might have to go back and try to use the AC method from step 1 again. Or maybe you need to change the factoring by grouping, and maybe you need to factor out a negative when you actually factor out a positive, that kind of thing. But remember that in this case, we're taking 3x plus 5, and we're going to factor it out. You can imagine it was being distributed from the right, so we're going to factor it out on the right-hand side. And that leaves you with the two terms. You can see it's in two terms, so we're left with two terms, a 2x and a minus 1. And there we go. We've managed to factor it into two binomials. And if you wanted to check your answer, you can expand this back out again. Now that's obviously going to be the most complicated way of factoring if you find a trinomial. It's much, much easier if the leading coefficient is a 1. But you're not always going to be that lucky. Sometimes, if you have a trinomial like that and the leading coefficient is not a 1, maybe you can find a common factor, and then you'll be able to factor that out, leaving you with a trinomial that has a leading coefficient of 1. Hopefully you're that lucky. I don't know. That factoring by grouping strategy as well, you might even be able to use that on its own. If you start off with a polynomial with 4 terms, see whether or not you might be able to group terms together and factor out a common factor. Not as common, but especially these quadratics show up all the time. And from my experience in teaching calculus as well, you're going to see lots of quadratics because the factoring for quadratics is typically a lot easier than trying to factor a cubic if you have an x cubed in there. So I hope that this has helped. More examples in class, and you'll be seeing this again in many more videos in the future because factoring is going to be a very key concept for simplifying otherwise gross looking expressions. I'll see you in the next video, and thanks for watching.